right, everyone. Thanks so much for joining. My name is Andrew. I'm a software engineer at Google, and I work on the Jetpack Compose runtime and compiler team. If you use Compose, then you work with the runtime and compiler. It's operating on all of your code, but chances are your relationship to it looks something like this. On one side of the spectrum, you write your code, and then stuff happens to it, and then a declarative UI falls out because of what the runtime and compiler do. This is a black box to a lot of people, which has its pros and cons. It's good because it means that a lot of this gets out of the way for you, but it obscures a lot about what's going on under the hood, and you might have ideas about what the Compose compiler and runtime are doing that it's not actually doing, and there may be things that it does that are unexpected to you. So with all of this, understanding what's going on under the hood can be really beneficial to making more informed decisions about how to design and develop your composables. So for today, we are going to walk through what the compiler and runtime are actually doing, and we're going to see that by stepping through a real-world composable and ultimately building up to what all of the compiled code for it looks like. The composable in question that we're going to be talking about today is this one. I've built a counter application here, and it works as just incrementing a sequence of tally markers here. So we've got a plus button to go ahead and increment, and then when we overfill the 5 tally mark, it'll go ahead and add another row here and start incrementing from there. This is about as simple of a composable as you can get. The code for it looks pretty much how you would expect it to. Removing all the styling information and getting us down to the bare bones of the composable, we end up with code that looks like this. This is going to be code that's really similar to what you've written before. So here we're taking in the name of the counter as a parameter. We've got some state here that we are remembering to store the actual counted value. And then we've got a column that's hosting the name of the counter, a button to increment the counter, and then these tally marker sequences. The way that I've declared the tally markers here is that I've got a for loop to handle all of the tally markers that are filled, and then an if statement at the end to handle the remainder for whatever portion of the tally, a portion of the count can't fill one of our 5 markers. From Compose's perspective, our goal here is to create a tree. The tree in question that we're making here is this one. What we're going to be doing here is we're going to create a tree of layout nodes. The column is going to be at the root, and then it will have children inside of it for things like the text, the button, and then some number of tally markers depending on how many we are adding inside of here. The goal for Compose is going to be to update this tree incrementally, and for the initial composition to create some version of this tree starting from scratch. We'll talk about the initial composition first, and then we'll build up and talk about recomposition and incrementally updating the tree. The first thing that we do when your code gets compiled is we add a parameter to all of your composable functions. The parameter that we're adding here is called the composer, and this is a synthetic argument that gets added to every composable function here. This parameter gets passed to all of the other composable functions that you invoked, which is one of the reasons why you can't call composable functions outside of a composable function. Composable lambda expressions are also composable functions, so they get the same treatment as well. They're also going to propagate the composer along all the way out through your composition hierarchy. For the initial composition specifically, your code doesn't actually need to do anything with the composer directly. We're going to see how the composer actually gets used there later on in the presentation. But initially, all that we need to do for our first composition and all that we need to do to create the layout node hierarchy is to emit nodes into the layout tree. We're not doing that directly from this composable function, so we don't see anybody calling the composer directly. But if we go a step deeper and dig into what composables like button and row and column do, eventually in Compose UI, you will call a function called layout. Inside of layout, this is the part of Compose UI that indicates to the runtime that you want to add a node to the UI hierarchy, and it does that by calling the compose node function from the runtime. Going a layer even deeper than this is where we begin to see the composer being used. The purpose of compose node here is to indicate to the composer that we want to inject a node into the hierarchy here, and we want to insert it wherever we are previously inside of the composition hierarchy. The implementation for this is to begin a group that corresponds to all of the content inside of this node. We then instantiate the node, which takes whatever user of Compose, the runtime that you've got. So for our purposes, it's going to be Compose UI, and it's going to be instantiating a layout node here. So we'll instantiate that, register that with the output tree. We'll do whatever updates we need to as part of recomposition or initialization. We will nest whatever content you've got, whatever other composable content you've got inside of this node to parent any children nodes to this node. And then we'll close out this group, wrap it up, and then exit, possibly adding other parents or siblings to this group. If you go even a layer deeper than that, though, you'll notice that we don't actually instantiate the node as part of creating node, as part of this create node function. The reason for that goes into one of the really core ideas of how the runtime and how Compose is conceptually designed, which is that when you do composition, you're not actually immediately building the UI. You're instead building a change list to describe all of the operations that, when executed, form your UI. So here, at the very end here, you'll notice that we're actually pushing an operation into one of these change lists. Typically, when we talk about recomposition or composition, we're actually talking about two separate things. We're talking about composition itself, which is the phase where your composable functions actually get executed. But in this phase, the composition is in a read-only state. The reason that we do this is because we're reserving the right for the runtime to have a lot of flexibility into how your composables get invoked. With things like pausable composition, it's possible for us to do things like do a partial composition, pause it, save it for later, resume later on, or even abandon a composition and restart it. So for that, we need to build a sequence of operations that may not be immediately realized. This is also why it's so important to use the side effect APIs correctly instead of having any externally visible effects inside of your composable functions, because they may not be observed, the results of your composition may not be observed at the same time that you're running your composable function. The other phase that we normally assume is part of composition is called apply changes. This is where we run through that change list and actually apply everything to the composition and realize the results of your composition. This is when the composition goes into an editable mode, and then once we start applying changes, we can't stop. There's no way of going back from this. So for the case of composition, how we can do things like abandon or restart if we wanted to, we don't have that same luxury with applied changes. If we fail here or can't complete, we have to do it exceptionally, and we need to throw away the entire recomposition. This is where all of the nodes actually get created. This is where the entire change list will execute, and this is where you want your side effects to be. With all that in mind, though, we've actually seen everything that we need to do to complete the initial composition. We've seen how the operations get built to define this tree that we're outputting, and if we only needed to output that initial tree once, we've handled it. We're going to see that there's actually a lot more moving parts that we need for recomposition. Some of those things are listed on this slide, which are that we needed to figure out, first of all, what part of the composition has changed. We want to evaluate our updates to this tree incrementally, which means that we need to know which portions of the tree are invalid and which ones we need to visit. We also need to figure out, on top of what part of the tree is invalid, we need to have a way of actually calling into that. The Compose runtime isn't magical or anything, it's just calling functions, and right now we don't have any hooks into your composable functions specifically. We have a way of calling the root, but that's not what we're going to want to do to do an incremental recomposition here. On top of that, we also need more information about what state is present inside of the composition hierarchy, and we need more information than what the Compose runtime has output. We need much more information about what the composition actually looks like before, and we're going to see other data structures that allow us to do things like storing values from remember and comparing in more detail what's actually happening between compositions. On top of all of this, we need to do this fast. This is something that happens on the main thread, and we have about 16 milliseconds to do it. So we are going to see performance optimizations work into all of the details that the Compose runtime and compiler add to your composable when it gets compiled. To To see how the runtime understands your composition hierarchy, we need to talk about the data structure that it uses. Here, this is a hierarchy of the composition, and it looks really similar to what we've outputted as part of our layout hierarchy. One immediate difference that I've added here is that we have a group for the counter now at the root, which we didn't have before. Counter doesn't immediately add a layout node here, but the runtime needs to know about it because it's going to be our re-entry point into the composition. We are also going to add all of the layout nodes that we output before into this tree. We want the runtime to be able to store them as well. So in addition to having the composition hierarchy, this is effectively also going to store a copy of the UI hierarchy that we're outputting. On top of that, we are also going to add space in this data structure for all of the remembered values here. And this is going to include parameters to your composable functions because we need to compare them to the previous composition, as we'll see, to check whether or not they can skip. So here, all of the parameters that are coming in are added to these groups here. And then there's only one explicitly remembered value here for the count, which is also going to be added to the group where we've added it here. One thing to bear in mind is that when you remember a value, the thing that we add to this tree is the remembered value itself. So in this case, even though count is a state, the object that gets added to this tree, to this group hierarchy, is the actual mutable state object instead of whatever value it holds inside of it. With that in mind, we can now talk about everything that we need for implementing the remember composable. When you call remember in your code and it gets compiled, this will be inlined by the compiler into code that looks like one of these two lines here. If you have keys, then we are going to compare them to what they were in the previous composition to see if your remembered value has changed from before. So here we are checking whether key 1 and key 2 has changed. We're going to check all of the keys that you pass in. If any of them are different, we need to recompute this lambda, and the runtime will take care of that for us. Otherwise, if you don't have any keys, then we can only calculate this once. We can only calculate the remembered value once and then reuse that for all of our compositions moving forward. I want to step back a little bit and talk about a very specific recomposition case that we have on our hands. The transition specifically from when the counter goes from 4 to 5. In our composable code specifically, the way that that works here is that we are actually going to go from a tally marker being presented by the if statement to one being presented by the for loop here. And one thing to bear in mind, because of some of the concept of compose, these two tally markers are different from one another. They're different from one another because of a concept that we call positional memoization, which means that different parts of the composition hierarchy are in different locations and need to have different state from one another. So even though one tally marker is going away and another one is entering, they're exiting and entering in different parts of the composition hierarchy and should not be reused. We don't want to carry any state between the two of them. What that looks like in this group table so far is that we initially have only one tally marker that contains 4. We are going to start recomposing column. We're going to visit the text, see that nothing has changed, make no changes to the composition hierarchy. We're going to visit button and see that nothing has changed and make no changes to the composition hierarchy. And then we're going to execute the for loop. When the for loop executes, it needs to add another tally marker before this other 4 that we've got before to have one of the filled items here. Then we're going to exit this for loop. We'll see that the if statement didn't execute, and then we need to remove this other group that we had previously, which is how composition is going to diff this recomposition for us specifically. This is all fine and good, but we have a problem on our hands, which is that we need a way of telling these groups apart. And right now, we don't have enough information to do it correctly. The reason that we don't is because when we're comparing groups like this, we will use the group metadata instead of doing any really deep comparison into the hierarchy. The main thing that we will look at is the key parameter, which gets introduced by the compiler. And because this is coming from the tally marker composable rather than the call site, these keys are going to be the same for every usage of the tally marker, which means that from the runtime's perspective, there's no difference between these two invocations of tally marker at this point, which is a problem because we need one of them to exit and another one to enter. So another thing that we're going to do as part of compilation is we're going to surround control flow blocks with other groups to keep their content separate from other content that appears around them. Here, because we never diff against groups that are outside of whatever parent that they're in or at different levels inside of the hierarchy, we can now group all of the tally markers that are filled and keep them separate from the ones that appear inside of the if statement. So now, instead of having the tally markers actually getting confused with one another, we can check and see whether the contents of the for loop have changed or whether the if statement has changed. This data structure that we've been talking about is now complete for what we need to understand. But I want to talk a little bit more about how it's implemented, because if you try and find this data structure, you won't find one that looks exactly like this. This data structure is called the slot table, and because it needs to be really, really fast because of how often we call into it, it has to look much different from how you would actually design this if you were writing a tree data structure in your application. The way that we implement this is we actually have two arrays to store all of the data inside of your composition hierarchy. The first one is a group data array, which is an integer array that is a bit packing of all of the group metadata. Again, we need this to be fast, so it is worth going out of our way, and we cannot afford to do things like allocating objects, so we have to do things like bit packing to be efficient enough to meet our frame deadlines. To store all of the values, both for the group data and for all of the slots that we use, we store this in a pre-order traversal linearized ordering of the composition hierarchy. So if you do a pre-order traversal and add all of the slots that are there, all of the values that we associated with these groups and the group metadata itself, you'll arrive at this ordering here. These two arrays are specifically implemented as a gap buffer, which means that this is a very condensed array when we create it, and there's some free space at the end. When you need to do a modification, we will copy that gap to wherever you are inserting content to make space for it, under the assumption that you're going to do more than just adding one piece of content or one group to the composition hierarchy to give you some space to make multiple operations in batch. Then when you finish with that, we'll do another array copy to move that gap back to the end. And similarly, if you remove content, we will shift all of the data over and copy everything to keep this as a densely packed array. I want to point out, if you paid very close attention to the title slide, you may have noticed that there is a 2025 edition stamp that's going on here. And one of the reasons why is because, like many of the details that we're going to talk about here, this is an implementation detail, and it's one that we're currently rethinking. We're not going to talk, we don't have enough time to talk about exactly how we are reimagining this. You'll have to figure out if we do another version of this talk later on. But if you're more interested into some of the concerns and some of the redesigns that we're considering, there's a CL that you can check out on Garrett. Going a step back, we should take a look and see how all of these groups that we surround the control flow with are injected by the compiler. We talked about how we need one for both the for loop and the if statement. So here, what the compiler does, recognizing that we have control flow that calls composable functions, it adds replace groups around the for loop and to our if statement bodies. The way that these replace groups work is that these are either added or removed. They are replaced, in essence. They don't get moved or repositioned anywhere inside of the composition hierarchy. There's another group that will do that. So the idea here is that something is either replacing the body of this if statement, or we are going inside of it and checking its contents versus the previous composition. This is also an example of where you'll see that key that I was talking about before. This is an arbitrary integer that's injected by the compiler. All of the groups that are in the slot table have a key that looks like this. This is a random-ish integer. It is defined, it is generated from the actual structure of your code specifically, so it is stable across recompilations, which isn't an important detail, but also bear in mind, these IDs are not unique. They are just random-ish and high-ish entropy to give the compiler and runtime enough information to effectively differentiate groups. We've talked about a lot of things and we've solved a lot of problems so far, but we still haven't gotten to the invalidation portion of the composition hierarchy. We haven't yet solved the problem of how we're going to invalidate a portion of our composition hierarchy. We've only talked about how we're going to do the actual diffing and observe the actual changes here. The answer to this question is two-part. One of the parts here is called the snapshot system. There's an excellent blog post series by Zach Klippenstein that goes into much more depth than we're going to have time to talk about here to give the snapshot system more justice than we can do here. But what you need to know for composition itself is that when you have state, it is backed by the snapshot system. And then when you start a recomposition, Compose takes a snapshot of all of the known state values. This snapshot includes what they were at some point in time so that if some other thread is mutating them, the composition can be consistent all the way throughout. The other thing that the composition will do with this snapshot is it will observe what values are read out of the snapshot, and it will keep track of where in the composition they are read. Then when the snapshot gets written to at a later point in time, the composition will also observe what values are being written to. And since it knows where in the slot table and which groups read those state values, it knows which ones to invalidate and can invalidate just the portions that read state that has changed since the last composition. This solves how we're going to invalidate part of the tree, but we need some way for Compose to call back into our content. And the way that we do that is with another type of group called a restart group. For all of your composable functions that are restartable, they will get a preamble and then a postamble that look like this. So we will create this start restart group function that indicates to the compiler, or to the runtime rather, that this is a composable that can be restarted. We will add all of the content to it, and all of the snapshot reads that happen inside of this restartable group get associated with the restart scope that we are creating here. At the very end, we call end restart scope, and we pass in this lambda expression to give the runtime a way to call this function again. We literally pass in a lambda expression that bootstraps back into the composable function itself. If you look really closely here, you'll also notice that this is actually a nullable call here, and this is because of a really clever and small performance optimization that the compiler and runtime will do. If you did not read any state inside of this restart group, then there's nothing to ever restart. There's no circumstance where this group can ever restart. If that happens, then this line here will bail out. You'll still get the restart group, but you will not get the restart scope, you will not get the recompose scope, and you won't get this lambda allocation to go along with it. So you'll still get the structure in the slot table, but we try not to allocate things if we know that there's not going to be a way to ever call into this code again. At this point, we've seen everything that we need to do to strictly handle recomposition. So now we can talk about what performance optimizations will appear inside of the code if you were to decompile it. The first one that most people know about is that groups are skippable, or composable functions can be skippable, which means that if all of the inputs are the same as they were in the previous composition, they won't execute. This is also code that gets added by the compiler to make a composable skippable. The way that this works is that all of the parameters are stored in the slot table and compared against their values in the previous composition. If any one of them changes, we'll execute your body, the body of your composable function, and recompose it. But if all of them are the same, we will literally bail out of your composable using an if-else statement. The entire body of your composable function would be stored in this else statement in this example here. Because of how these parameters get propagated through composables, there's a pretty high likelihood that we've already done a comparison for a given parameter and are propagating it down to another composable here. So another optimization that goes along with group skipping is that we add another parameter to your composable, which is this changed parameter, which offers hints to the skippability logic of your composable for whether we've done comparisons on any of your parameters before so that we don't compare them again. The way that this works is with a whole bunch of bit arithmetic. The way that they are packed together is that all of the arguments in your composable function get 3 bits inside of this changed mask here. The lower bit and the upper bit are reserved. They're not used because 32 does not, in fact, divide cleanly into three. But for your first 10 parameters, all of them will be stored. All of them will get 3 bits going from lowest bits to highest bits inside of this mask here. If you have more than 10 arguments, you get another change mask for however many arguments you need here. Inside of one of these bit masks specifically for one of the arguments, these 3 bits correspond to both the stability of the actual object itself, which doesn't really matter for our purposes, and also the comparison state when it's known. It can either be uncertain, which means that we haven't done the comparison yet. It can be the same, which means that we have done the comparison and it was the same as it was in the previous composition. It can be different, which means that we, again, have done the comparison before, and it was different, and we cannot skip this group. And it can also be static, which is one that you may not have seen before. This is a special argument that is injected by the compiler. If you have a runtime or a compile time constant that you are passing in for any one of the arguments to a composable function, it can be marked as static, which means that it is known to never change, and we never need to do the comparison under any circumstances for it. So transforming the bit masking logic that we had before into something more understandable, the skippability logic looks something like this. We first decompose the actual change flags for each of the parameters. In this case, we only have one that we care about, and we check to see if it's something that we've already compared before and if it has a known stability. If it does, it has a known comparison state, then we will go ahead and use it. Otherwise, we will compute it here and then generate whatever that flag should have been for this value. After we have all of the dirty mask in place, we will then check and see if any one of them is different than it was from before. If it is different, we can't skip, we evaluate your function. Otherwise, we just skip, we fully accept the group as it was before and continue recomposition with wherever we were before. There's one other performance optimization that will appear inside of your compiled code, and then we can talk about what actually happens and we can see all of the code that gets compiled. That last optimization is around Lambda memorization. Compose is very Lambda friendly and they appear all over the place. And we have 2 optimizations for Lambdas depending on whether you have a composable Lambda or a non-composable Lambda expression. For composable Lambda expressions, we introduce this remember and updated, similar to remember updated state, but a more lightweight version of it that's more bespoke to composable Lambda expressions. The idea here is that we create a wrapper object that stores a reference to the composable Lambda that you have. And then if you change the instance or recompose and get a new composable Lambda expression, we only invalidate the people that actually called the composable Lambda expression. If nobody does and you get a new Lambda, then we don't recompose we don't invalidate any of the users of it. If you create a composable Lambda expression, pass it 18,000 layers deep, and then invoke it, we only invalidate that leaf node containing the actual invocation to the composable Lambda expression. For regular Lambda expressions, these will literally get wrapped inside of a remember block when you instantiate them inside of your composition hierarchy. If they capture values, those will be passed as keys to this remember block here. And if you if you have the same Lambda expression that is always the same, then it can be compiled into a singleton. So the idea here is that we want to invalidate only the regular Lambda expressions only if the Lambda expression actually needs to change here. So they get optimized even a step further than composable Lambdas. With that in mind, I will stop teasing. We have now seen everything that we need to understand all of the transformations that happen to your compiled code, or that happen to your composable as it compiles. So let's talk about what happens. And unfortunately, I cannot fit this on this one slide, so we will be doing a lot of scrolling here. At the very beginning, you'll see that we have the restart logic that we had before and the skippability logic that we had before, in addition to all the parameters that we injected here. So we have our restart group. We also have this source information group, which we haven't talked about yet. This is used for debugging and the layout inspector. If you're doing a release build, this will get stripped out by R8. If you're using R8, please use R8 to get rid of stuff like this. If you are in a debuggable build and you're not doing things like enabling the stack trace information that we've added very recently or the layout inspector, this is actually a no-op. We only capture this when we think that you're going to need it. After the source information, we have the skippability logic that we had before. Again, literally an if-else expression where all of your code lives inside of this if statement. Inside of here, we have the remember block to save the mutable int state from before. We also have this trace event here. This is also going to be used, this is also introduced by the compiler, but instead of being used for debugging information, it is used for performance information. This is kept in release builds. So if you want to do something like run assist trace or get a perfetto trace of this, all of the trace events are available for you in release builds, even if you're using R8. If you don't want these, you can configure R8 to get rid of the trace event, which will save you a little bit of bytecode, which is nice. Moving along, we have the composer.cache that we talked about before. It doesn't take any keys, so it's going to create the state once and then continue to reuse it. We have the column that we declared with our main content inside of it. It had a composable lambda, so we will go ahead and remember it. And then inside of this composable lambda, we again see more skipping behavior because this is, again, another composable function that is being transformed. Finally, we have code that looks like we actually wrote it ourselves, which is the text composable, which gets called pretty much as is, just passing the other arguments that it requires. Similarly for button, we do more of the lambda optimization here. The first lambda expression is our on-click listener, so we will remember the count incrementer here, and we can reuse it because the captured value never changes. Our composable lambda here, interestingly, is a singleton. It does not change ever in the lifetime of the application across any of the usages. It always just displays the plus icon here. It is the same composable always, so it gets compiled into just one object that gets reused across every invocation of this composable. Next up, we have the for loop, which again gets wrapped with a replace group to keep it separate from the other control flow blocks that appear outside of it. We've got our tally marker that again gets called pretty standard for the other composable functions here. We've also got the if statement that appears with the other groups surrounding both of its branches here. This is an implementation detail, and again, one that ties back to this is what it looks like today. It could change in any release here. The groups that are generated by the compiler are implementation details. We will do the right thing to make sure that we can differentiate all of your composables from one another, despite whatever you may do inside of your composition hierarchy. But we've spent a lot of effort reducing the number of these and injecting them very strategically. So currently, we will actually inject another else statement here and then introduce another empty group inside of this. This will be different depending on which version of the compiler that you're using. To close things out, we will skip over so many closing curly braces and then corresponding ends to begins that we don't have time to talk about. And then we will end with the other end restart group that we've talked about before to give, again, the runtime a hook back to call our composable when it needs to be invalidated. And with that, you are an expert at understanding what the compiled code of your composable will look like. All of the transformations from the compose compiler that get applied to your composables. There's a couple of other details that we didn't talk about that will build on top of all of the ideas here. First of all, if you're looking at the actual bytecode itself, you'll notice that the function body here is substantially larger for a number of reasons. If you were to actually take this sample in the real world, and we lost video. Pausing for AV. This is not part of recomposition. All right, I think we did it. Other things that you will see inside of your compiled bytecode here, this is a much smaller scoped example that only includes the bare minimum of what we needed to understand this specific example. But in the real world, the composables that you call, a lot of them will get inlined and will introduce their code into the bytecode as well, especially the layouts like column and row. They will actually inject even their layout policies into your composition. So you'll see those in the bytecode if you were to decompile it. Also, pretty much every composable function is actually going to take modifier as well and have defaults, which have other details that the compiler needs to add for them as well. These will build on top of and look really similar to a lot of the other flags that we introduced to the compiled variations of our composables as well. And then there's a lot of other features in the runtime and compiler that build on top of all of these details that we've talked about so far. The runtime especially has so many creative ways of using groups and moving them around and nesting composition as well. All of them build on top of how do we use the slot table and how do we define this as a composition hierarchy, track it, and diff it across recompositions. If you take away anything from this presentation, let it be this slide. First of all, when you are doing a composition itself, when you are recomposing, we create a change list and we apply it at some point later on. This is why it's so important to use side effect, and this is influencing a lot of the behaviors that the runtime can add in the future around scheduling how your composition and how your composables execute. The other thing to bear in mind is that from the runtime's perspective, we need to know about control flow groups, not composable functions. So when the compiler and runtime are operating on all of your code, we care about the groups that get generated, which is why it's one of the reasons why it's so easy to refactor your code into other functions, because for the understanding of your code, the function borders don't really mean all that much to us. They can introduce layers for restart and skipping, but they don't impact our understanding of your code. The other thing that I want to talk about is that the runtime and compiler are not magical. They are doing a lot of things, and they have a lot of really smart design that is going along for the ride, but they are not magical, and they don't actually understand fully what all of your code is doing, which means that we are not trying to optimize any of what's going on inside of your composable, other than the smaller optimizations that we will do as part of compilation and during the runtime here. To round everything out, in 10 minutes or less, we're going to do a quick lightning round of some small performance optimizations and things that you can bear in mind with all of this information. The first thing that I want to talk about from our perspective on the Compose engine team is that a lot of people, when they talk about composable reperformance, fall into this trap of looking at how many times their composable is called and recomposed and using that metric. This is a really easy metric to get, which is one of the reasons why people gravitate towards it, but it's not necessarily a very useful one because it doesn't tell you all that much of the story. Recomposition is not evil, but if you can do something without recomposition, you should try and do that. We've lost the slides again. I'm going to keep going on in the interest of time here. Recomposition is for when you need to make structural changes to the UI hierarchy. If you need to do that, you should not try to sidestep recomposition or bail and try to make something skippable when it shouldn't necessarily skip. If you do want to do less in composition, you should move your work into layout and draw here. You can also be a better citizen with recomposition by making sure that we are only invalidating the parts of your tree that need to be reinvalidated. The best way to do this is to actually benchmark and profile your code, which is the boring standard answer of it depends for performance. If you want to update the tally marker, if you want to turn our composable that we've been talking about into one that doesn't need to recompose, you can do that. The way that you would do that is you would need to update the tally marker so that instead of showing one tally marker that goes up to 5, you would need to update the composable so that it can show any number of them. You would also update it to take, instead of the count as a parameter here, you would take a lambda expression that returns the count instead. The reason that you do this is because you can move the snapshot state read into layout and draw, which are also snapshot observed. And if you do that, it will invalidate just the layout or just the draw pass. And this is great because if we do this, we can now correctly increment the counter and only invalidate layout and draw because we don't actually need to update any of the UI hierarchy if we design our composable in this way. Another quick win that you can look out for is what's known as backwards writes inside of your composition. There's a really trivial example, and then there's an example that people do all the time here, which is if you have a state, use it inside of your composition, and then also update it inside of the composition. What you have done here is you have invalidated something that you just worked on inside of your composition here. So even though we have created the tally marker, we have now updated the count here, which immediately schedules another recomposition for the tally marker and will schedule another frame here, which is really wasteful and will defer the observed results by a frame here. Another really common example that people will use is observing values from their layout inside of composition. This is really easy to do and it's really enticing to do, but this has a lot of the same problems where you are now introducing another frame delay between when your composition actually gets the observed values from your layout, and you're trying to read values from a future state in a previous one. So if you find yourself gravitating towards code like this, try to think about what other ways you can do to avoid introducing a backwards write like this, and depending on layout data inside of composition. The last thing that I'll leave you with is that performance is always on our mind for all of the Compose teams, especially the runtime and compiler. A lot of the times you can get benefits just by updating the dependencies. Runtime is a dependency that's not really coupled towards anything, so it can be very easy to update on its own. The compiler can be a little bit more involved because it does require updating your actual Kotlin compiler version, but it can give you some really quick wins. So if you're a couple of versions behind, I would recommend updating to see if you get any performance wins. Another thing to bear in mind is that the compiler has different behaviors depending on which version of the runtime is actually present in your compile time class path. We will give you better behaviors for the compiler if we see that there's a newer version of the runtime present. You can update the runtime on its own. It will have a much smaller impact, but it will impact everything as well. So keep your code up to date, use RA. The video will be posted later on for you to revisit the internals here. Thank you so much for coming out.